Hey guys, welcome back to our next episode of What in the Heck is Going On When We Dissolve Things. Today we're going to take a look at two different big concepts. We're going to cover two of our different standards. Number one is the concept of concentration. We're not going to do the math part yet. Math comes up in D and E, but we're going to just talk about kind of what concentration is. And then number two, or number C, or letter C, whatever, we're going to talk about how fast things dissolve and how do we kind of deal with how quickly things can get into solution. So those are our two big ideas that we're going to do today. So concentration and rate of dissolution. So our rate of solvation. Right? So in the last one, we talked about kind of what a solution was, what the parts of it were, some basic vocabulary. So a solution is a heterogeneous mixture of two different components, at least two different components. You've got the solvent, which is the bigger component, and it does the dissolving. And you have the solute, which is the smaller component and generally looks like it disappears. So those are the two things that we've got. We're also going to deal with the term aqueous today. I mean, that kind of comes up in all of these solutions. For the most part, the chemistry that we're going to do is going to come along with aqueous solutions because water is a very a very safe solvent for us to use. Luckily for us, we don't dissolve when we're exposed to water, not for too much anyway. You ever wonder about why that is? Anyway, so we're going to deal with aqueous solutions today. So again, we've got solute, solvent, and solution, and how we can kind of moderate what's going on in solutions. So number one, we're going to talk about this concept of concentration. And I don't mean thinking real hard, obviously, but concentration in the chemistry sense. And you guys have good experience with concentrations. You guys have probably made Kool-Aid or lemonade or coffee or tea or something from a mix, and you know that there's a difference in ratio between how much water is in there and how much of the good stuff is in there, the solute, right? That if you put not enough in there, it just tastes like water. If you put too much in there, sometimes it tastes great, sometimes it tastes like too much, like lemonade, blah. And then sometimes you can put so much in there that you can't even get it all to dissolve, right? So this concept is called concentration. There's two main words that we use to kind of generalize between concentrations, and this is a range. They spread together. On the one hand, we have a solution that could be considered dilute. Lots and lots of water and very little of the solute. On the opposite end of the spectrum, we have something called concentrated, which has lots and lots and lots of solute and relatively little solvent. So again, we would kind of call them strong and weak if you're just using like, oh, that lemonade's really strong, or ooh, that tea is really weak. That's the terms that we use for solution concentrations, concentrated and dilute. We're not going to use those terms here because the terms strong and weak are actually used for something very specific when we talk about acids and bases. So that's why you're not going to hear me use those particular terms. I will use the terms concentrated and dilute. So dilute means there's lots of water and relatively little of the good stuff, and concentrated means there's lots of the good stuff and relatively little of the water. And again, they blend together. So you can't just look at a solution and say, oh yeah, that one's concentrated. You have to compare it to something else, some sort of a standard. What's kind of handy for us, we're going to take advantage of in lab, is that if we're using colored solutions, the different colors can actually give you an idea of how concentrated those solutions are. As you probably can figure out just from experience, that the darker a solution is, the more solute is present. The lighter or clearer a solution is, the more solvent is present. This principle is actually something known as Beer's law or the Beer-Lambert law. It's more fun to call it Beer's law, I know. So we're going to actually do a lab on this tomorrow based on this concept that if you know what these solutions are because you've tested them or you made them yourself, then you can actually take an unknown solution and compare it color by color and figure out exactly what it is. It's a linear relationship, comes out nice and neatly on a graph for the most part, and you can actually figure out the concentration of an unknown solution just based on its color, how much light gets absorbed. And again, if you take a look at these, any of these, doesn't matter which one it is, think about how much light's passing through this lightly colored solution versus very little light is passing through a dark solution. We're going to use something called a colorimeter that can just measure that precisely. It's called percent absorption sort of thing. So anyway, Beer's law. So getting a little bit more on this, when we're talking about the amounts of stuff that are in there, I don't know about you, but at some point in time in your life, if you were making Kool-Aid or lemonade from powder or something like that, you thought, I just want it to be a little bit stronger. Maybe it was your Tang, right? And you just kept putting the Tang in there, right? And you kept stirring it. At some point in time, you get to that point where just no more of it will dissolve, right? You just get like solid crystal Tang at the bottom. Yeah. Now it's blah, but when I was a kid, I used to love that. And so there's terms that we use for this idea of being saturated and unsaturated. So the term saturated means that the solution is holding absolutely as much of the solute as it can. Think about a saturated sponge, right? It is so wet that you try to scoop up any more water with it and it's just going to run off the side. Well, in this case, the solvent is kind of acting like a sponge. So it can be holding as only so much of the solvent, and any more that you add to it simply just going to run off. So like this picture up here in the top, I know it's copyrighted picture, so I stole it. But this picture over here in the top would be a saturated solution, right? This solution up here, even though it's crystal clear to us, it's got this solid that's at the bottom. It just cannot hold any of that. On the other hand, the solution here on the left, which we would assume still has stuff dissolved in it, would be what we call unsaturated. It's not holding the maximum amount. If you added another spoonful, you could probably dissolve it in there. So that's the concept of saturated and unsaturated. There's some differences to this in terms of how do we know when something's going to be saturated. Well, over time people have worked out these things called solubility curves that allow us to predict or calculate exactly how much stuff can dissolve in a solution. And you get a graph that looks like this. They're not straight lines, they're always some sort of curve. That's why we call them solubility curves. So if you look at the axes to this really closely, you can kind of see how this is read. So what we've got down at the bottom is this idea of temperature, and I'll mention this in a second. And over here on the side you have this idea of solubility. And if you take a look at the units here, it's how many grams of solute can dissolve per 100 grams of water, basically. So again, we're going to use the same size water every single time. We can't just have like a lot of water and a little water. So they standardize it to say out of 100 grams. And so you can kind of read this line. This line that's on here, the green line, is for a particular salt. This one is potassium nitrate, KNO3. And the green line tells you the saturation line. So if you're right at 20 degrees, and I'm going down here to the bottom, if I trace up on the graph to that line, I can see that at 20 degrees, approximately 35 grams of KNO3 should be able to dissolve in there. So that's kind of how you read this. You go from temperature and then you read over to the other axis to figure out how much could dissolve. What's the solubility of KNO3 at that particular temperature? So if I try to put more than 20 grams in there, this stuff, if I try to go up to this part, if I tried to put like 50 grams in there, it can't hold it. It's saturated at 35 grams. If I try to drop 50 grams in there, the excess is simply going to drop to the bottom and remain undissolved. If I go less than that at 20 degrees, like only 20 grams at 20 degrees, I'm under the saturated line. That means I'm unsaturated, right? And it would actually be able to hold more. It's going to all completely dissolve and it's just going to look like a clear solution. So there's an example of a problem that you can do on here. What kind of solution would be created if you dissolve 70 grams of KNO3 in 100 grams of water at 30 degrees Celsius versus at 60 degrees Celsius? So here's how you would kind of attack this. You would look for 70 grams of KNO3 at 30 degrees C. So what I would do is I'd go over to my graph, I'd find the 30 degrees C line, which is right here, the 30 degrees temperature line, and I'd trace up to where it crosses that saturation line. So if you look at the saturation line, it looks like it's about just under 50 grams can be held. So again, right here at this spot, I should go to my little there we go, my little enhancer, right? So if I go to this little spot, 30 degrees C, I can hold just under 50 grams. So what's going to happen if I try to put in 70 grams? Well, again, if this is the saturation line and I'm trying to put this much in here, that means this amount above the line would all fall to the bottom. So about 20 grams would fall to the bottom. It could hold about 50 and the other 20 would simply sink. All right, second half of the question, what would happen at 60 degrees C? Okay, well, if I go over to my 60 degrees C and my saturation line's all the way up here, 60 degrees C, man, I can hold a lot more up there. That's over 110, maybe 115 grams that could dissolve in there. And I'm only trying to put 70 in there, so I'm like at that spot right there. So 70 grams at 60 C, it's under the line, so that would be an unsaturated solution. So yeah, you can see that temperature has a big role here. The higher the temperature, generally the more that can dissolve, right? Solubility goes up as temperature goes up. So this is called a solubility curve. This next graph can be kind of overwhelming. I'm warning you that it's coming. Okay, wow, woo, look at all that graph, craziness, right? It turns out each substance has a unique solubility curve. So the one we looked at on the last graph was KNO3. It's this light blue line on this graph, and now you can see all kinds of other substances on here. So take a look at some of these different shapes and levels and things like that, and you can see there's lots of different salts and things that are on here. Some are more soluble and some are less soluble. So for example, table salt is this one, this kind of this brownish one, is kind of relatively stable across temperature. It doesn't really change much. And it's actually kind of relatively low. It doesn't really hold that much compared to KNO3, which is this light blue one, starts low at cold temperatures, can't hold a lot, but man, warm it up a little bit, and that solubility shoots way up, and it can hold a whole bunch. And you've got Ki, which is like off the chart, it can hold so much on there. And again, you've got like kind of everywhere in between. There's a few weird ones. Most of them do show an increase, right, as you go from left to right in temperature. As temperature increases, solubility increases. There's a few exceptions. This gases like ammonia and SO2, sulfur dioxide, actually decrease. That's kind of a little weird thing. But for the most part, if you remember the pattern that increasing means that you are increasing temperature means increasing the solubility, you've got the right idea for most things. One more important point that we can get from this. Saturated and concentrated do not mean the same thing. Same thing, unsaturated and dilute do not mean the same thing. So here's what we're talking about. Saturated means it's full. That doesn't necessarily mean that it's holding a whole bunch of solute. So I'm going to look at this KNO3 line because it's this bright blue one. So if it's a cold solution way down here, if you've got 100 grams of water, it's only holding about 20 grams of KNO3. That's relatively dilute. There's not a lot of KNO3 in there. However, that's as much as it can hold. So it's dilute, but it could be saturated. If we go up to the other end, take a look up over here, man, these things are crazy. If you're going up to these higher temperatures, like we're at 60 degrees or 70 degrees along this one, you've got 100 grams of water and way over 100 grams of KNO3 here. So this is concentrated, but if I put 100 or 110 grams in there, it's not even saturated yet. So those concepts are kind of related, but kind of not. You've got to be really careful with the idea that saturated and concentrated are not the same thing. Those things depend on which material you're talking about. Saturated and unsaturated kind of depends on which salt it is. Concentrated and diluted is talking about how much of it's in there, not whether it's saturated or not. So again, just a little bit of caution, and if you kind of take a close look at this slide, you might be able to see some other examples of this that are actually kind of weird. Okay. Moving on, this idea of temperature is sort of interesting. You probably know that if you heat up a solution, it's also going to dissolve faster. Most people will tell me that if they want to get something to dissolve, heat it up, right? Well, heating up a solution does two different things. Number one, it will dissolve faster, but number two, it can also dissolve more. So there's two different things going on. The first half of this lecture, we're talking about concentration, that idea of how much can dissolve. And in these last couple slides, we're going to talk about how fast can it dissolve. So this is rate of dissolution. And temperature affects both. It affects the amount that can dissolve as well as the rate. Now, why does it get faster? It gets faster because hotter water means the water molecules are bouncing around really quickly, so those water molecules can come into contact and pull those ions out much more quickly. And so that's why it happens faster. You know there's some other things that also affect the rate of dissolving as well. For example, stirring. You know that if you want to make your Kool-Aid faster, you don't just dump the sugar in there and let it sit at the bottom and then stare at it for an hour like, I'm thirsty. You actually sit there with a spoon and you stir it up, right? Well, the reason why stirring makes dissolution happen faster, or solvation happen faster, is because as you're stirring it, you're bringing fresh solute molecules into contact with those solvent molecules. I said that backwards, didn't it? Well, it's both, actually. If you're stirring it up, you're actually kind of taking those solute molecules and spreading them throughout, and you're bringing more solvent molecules into contact with the solute. So a little bit of both, depending on whether it's just one single chunk or whether you can just get it all stirred up. But anyway, you're getting that idea of kind of getting everything. You're stirring the pot, right? You're getting everything into contact with everything else, sort of agitating the system and allowing that diffusion process, that solvation process to happen at a much higher rate because it's happening throughout, not just on the surface. Okay? And then there's the third one, the last thing. There's three things that affect the rate of dissolving, by the way. Number one is temperature, number two is stirring, and then here's number three. This is the trickiest of the three, that's why I put it on its own slide by itself. The third thing that affects the rate of solvation, or the rate of dissolution, depending on how you want to say it, is something called surface area. It's how crushed the object is. So do you have 10 grams of ice in one big cube, or do you have 10 grams of ice crushed up into much smaller bits? And I don't know if you recognize this, if you've ever done this with sodas before, that if you put crushed ice into soda, it will cool the soda down much faster, but it will dilute the soda, right? The soda will get all watered down much more quickly. If you put crushed or big cubes of ice into soda, It won't cool it down very fast, but it also won't melt the ice as fast. This is that idea of surface area playing a role in here. So again, remember what happens when we're trying to dissolve something, and I'm not talking about melting here, I'm actually talking about dissolving. Assume that these 3 blocks down here have the same amount of mass, same stuff. So it could be one big block of salt, big block of ice, whatever you want to call it. In order to dissolve something, the solvent has to come into contact with it. And that can only happen on the surfaces, only from the outside. So if you think about this one big block, there's only 6 sides that that solvent can come into contact with. If I start subdividing this, crushing it, breaking it into smaller pieces, now look at all these new surfaces that are being exposed. I'm increasing the surface area and I'm allowing more solvent to come into contact with the solute at exactly the same instant. If I subdivide it even further, really crush it down, not just like chunk it up, but like powder it, then we can say all these little particles are coming into contact with the solvent at the same time, and it really increases the rate. Crushing it, surface area, does not change the amount of it that can dissolve. There's no difference in terms of solubility. What happens is, in the first case, it's going to dissolve slowly, but in the last case, it's going to dissolve quickly. That's the only difference, not the amount, just the speed. And again, the reason why is that if I take that one piece and powder it up, now there's tons of surface area available, and all of that solvent can come into contact with the solution. If you combine that then with mixing and then with temperature, that's how you make a solution dissolve, make a solution very quickly, or make a solute dissolve very quickly. So there you have it. Those were our big ideas from today. I kind of reviewed the parts, solute, solvent, and solubility. We talked about how temperature affects solubility, the fact that each thing has its own rate of solubility as well. And then we started to talk about the 3 things that affect it. So we talked about concentration, we talked about solubility curves and how to kind of interpret a solubility graph, and then we talked about the 3 things that can make dissolving something happen faster. So there you go. We'll go dissolve some things in class tomorrow, and we're going to do a lab on Beer's law, concentration and color. Have a good one. See you in class.